Namaste to all my dear students. I welcome all of you in Anti-White's YouTube channel. This lecture will be beneficial for MSc second semester students who are studying statistical physics. Today I will discuss with you an important topic which is Nernst theorem. But before discussing about any theorem, I want to tell you that we must cover its important sections like when and who gave the theorem. Second, its qualitative and mathematical statement. Third, its proof. And fourth, which is the final part, is their significance or applications. So let's start with Nernst theorem. This theorem was given by W. Nernst in 1906. Its qualitative statement is like that. The entropy of a system is zero at absolute zero. Mathematical illustration is so simple, which states that at T is equal to 0 Kelvin, entropy is also 0. This theorem can be proved in quantum statistics only. We know that specific heat at constant volume, which is denoted by Cv, is equal to curly Q upon curly T at constant volume. And this curly Q is equal to T curly S. Similarly, specific heat at constant pressure, which is denoted by Cp, is equal to curly Q upon curly T at constant pressure. And this curly Q is equal to curly Q is equal to T into curly S. First law of thermodynamics states that dq is equal to du plus dw, and this dw is equal to pdv. dq is heat content supplied to the body, and du is internal change in internal energy, and dw is the work done on or by the system. Similarly, second law of thermodynamics states that change in entropy is equal to change in heat divided by absolute temperature. On combining these two laws, a combined form can be represented like that. This dq is equal to tds is equal to du plus pdv. Here internal energy U, this is sum of kinetic energy and potential energy. In case of an ideal gas, this internal energy U is function of temperature only. But in real gas, internal energy is function of temperature as well as pressure. But in both cases, it is clear that internal energy is the function of temperature and increases monotonically with the temperature. Conversely, when the temperature falls, the energy decreases. When the temperature falls, the internal energy decreases, whether the case is ideal gas or real gas. At absolute zero, that is temperature is equal to 0 Kelvin, the body or system must have minimum energy. At 0 Kelvin, the system has minimum energy. Now let's divide the system into different parts like this. Suppose this is a system or a body, and we divide it into different parts, number 1, number 2, number 3, number 4, and so on. These are different parts of a system. Now at 0 Kelvin, each part of the system or body is in particular state having minimum energy. At 0 Kelvin, each part has minimum energy. In other words, each part is in the ground state. Ground state is the state of minimum energy. And this is the ground state of part 1, this is the ground state of part 2, 3, and so on. So we can see in this figure that there is only one quantum state. There is only one quantum state, and that quantum state is ground state. This is only one quantum state in first part, second part only one, third part, and so on. So in all parts of the body, there is one quantum state and which has minimum energy, which is also called ground state. We know the number of quantum states is called statistical weight. This is called statistical weight. More precisely, the statistical weight of each part in this case is unity. And this is happening only when T is equal to 0 Kelvin. Suppose that statistical weight of first, second, third, and fourth parts are represented like that: 1, 2, 3, 4, and so on. Then the statistical weight of the entire body. Then the statistical weight of the entire body will be the product of the statistical weight of its parts. Now this statistical weight, value of this statistical weight in each part is 1. This 1, this 1. So we can write like in first part, statistical value of statistical weight is 1, second is also 1, which is ground state, third is also 1, and fourth is also. So product of the statistical weight of the entire system comes out to be 1 or unity. From the statistical definition of entropy, S is equal to K log of statistical weight, where this K is Boltzmann constant. This is statistical definition of entropy. Now at temperature 0 Kelvin, the statistical weight of the entire body comes out to be unity. So S is equal to K log and statistical weight is equal to unity. So log 1 is equal to 0. So K into 0, which is equal to 0. So at temperature 0 Kelvin, entropy is 0. Because the statistical weight or number of quantum states of the body is only 1, and which is ground state. Hence at T is equal to 0 Kelvin, S is equal to 0, which is Nernst theorem. This is its proof. Thanks for watching and listening. In next lecture, we will discuss about the significance or applications of Nernst theorem.